Hi everyone, good morning to all. Let us start the today's class. From today onwards, we will have new chapter titled as metal clusters. Metal cluster. From the title, we have to know. We will come to know that what would be the whole chapter. As such that the title of book defines the what the book it has. Similar to that, what I believe that the name of the chapter will refers the all the topics covering in it. So with that point of view, here I will just define the what would be the metal cluster title. Once I want to brief. So here in title of metal cluster, it is an two words. It has two words such as metal and cluster. Where is metals? What it means by metal? Metal is an atom with electropositive character. Atom with an electropositive character will known as metals. That's known to you. When it comes to a cluster, cluster meaning is a close group of things. Here we will have, instead of things, we can also add atoms to have proper justification in metal cluster word. I will say that it is a cluster is a group of atoms, right? So in including of metal cluster, so here it may be a group of metals. Metal cluster nothing but a group of metals. So it may not be a simple group of metals, right? The chapter and whatever we expect from the inorganic chemistry, it all about the complex chemistry, right? Most of the inorganic topics will be related with complexes, such the metal cluster as an inorganic topic. These also mostly related to complex topics, right? So as it is the title of metal cluster, group of metals with the simple titles of metal and cluster, simple meaning of metal and cluster, it can be said that the complex in which the existing group of metals, right? Such may be the title. From the title you will come to know. So in this title, what the topics it may covers, if we look into that. So if we go for the coordination chemistry, as we learn in intermediate in UG level, coordination chemistry, the coordination chemistry, it defines as complex. It has the topics of definition of complex, and it follows by classification of complex and structural theories to define the structures of the complexes were covered in the coordination chemistry topic in intermediate or UG level. So same to that, with the same expectation here, complex the metal cluster chapter also will consist the metal cluster definition and followed by its classification of metal clusters, and there it followed by the structures of those different classes of metal clusters will be there, and here and there is some structural related characteristic phenomena also we can observe. These are the topics will covers into the metal cluster chapter. So now let us go the chapter, right? Let us start the chapter with the definition of metal clusters. Definition. The metal clusters are the complexes with two or more metal atoms which are having direct and substantial bonds, right? So as we expected, the metal clusters, they are the complexes. In definition we will come to know this. They are complexes where they has multiple number of metal atoms, two or more than number of metal atoms, and thus metal atoms which having a direct and substantial bonds. So complexes with multiple metal atoms having metal to metal direct bonds and substantial bonds is known as metal clusters, right? So when it comes to the two words in definition we have to point out, that is direct is a word and substantial is another word. Direct, which means the metal to metal direct contact bond has to be take place, right? For example, if we go right before this metal clusters, right, we come to know a single metal complexes, right? Complexes which have we seen before metal clusters are having only single metals. Where it come to now, from the metal clusters chapter, you will come to know that there are the complexes which has multiple metal atoms, right? And before this metal clusters you might see single metal, or highly you are seeing two metal complexes, right? More than two metal complexes you might not be seen. From now onwards in the metal cluster chapter you will come to know number of metal atoms in complexes, right? So you might see then complexes such as tetramine copper 2 sulfate, which is an one metal complex, right? And you might also see binucleus metal clusters such as tetramine cobalt chloro chromium pentaco. As you find this complex, is you come to know what is this complex. It is an conjugate base complex what we observed in SN1CB mechanism. Before the metal clusters we have know that single metal complexes, and such as these dimetallic complexes, dinucleus metallic complexes, where when it is these two complexes is related to our metal complex definition, if we see these are totally different from the metal clusters, right? How does they differ is, in metal cluster it is said that complex with two minimum or more than two metal complexes has to be exist, right? When it comes to the first complex tetramine copper 2 sulfate, it is having only one metal, so this may not be metal cluster. When it comes to the second, right, it may having two metals, so this may be closer towards the metal cluster, but it is not actually the metal cluster. Why? Because the metal cluster is complex with two or more metal ions, and thus metals has to have direct and substantial bonds. Where it here, right, dimetallic complex, it not having direct metal to metal bond, where the metal to metal linkage is with the help of one bridging ligand. The chloride is bridging two ligand parts, sorry, two complex parts, right? This is one of the part of complex, this is another part of the complex, and thus two metal are bridged by the chlorine ligand. Such bridging metal complexes never comes under into the metal clusters, where The metal cluster has to be a complex where it having two or more metals, and thus metal has to have direct and substantial bond. Where it here direct means, when it comes to an example of octacarbonyl di-iron complex, octacarbonyl di-iron complex, when it comes, right, this complex has the structure of iron to iron single bond, where two irons having each 3 carbonyls bonded in terminal, and the other two, sorry, 9, it is 9 carbonyl, the other 3 carbonyls are bridging between two irons, right. So here it may having a bridging ligand site to bind iron to iron, two iron atoms, it has bridging carbonyl. Instead of bridging carbonyl, it also consisting one direct metal to metal bond. This is what the important, right. The difference between second complex to this complex is it having a metal to metal direct bond. Having the direct metal to metal bond indicates this as an metal cluster. So this may not be metal cluster. Such direct metal to metal bond, when it exists in a complex having multiple number of metal complexes, metal ions, will be known as metal clusters. And the definition of direct you may now come to know exactly, and what it means by substantial. Substantial means, the substantials means having importance, for metal to metal direct bond. And here it means, that means the metal to metal bond should define the physical or chemical character of metal cluster, right. The substantial means the metal to metal bonds should gives the physical and chemical properties of the metal cluster. It has to have importance to give its metal clusters physical and chemical characters, right. So here when it come to them, nonacarbonyl di-iron complex, the complex structure is indicated as linear structure. Thus linear structure, from where it is defined as linear structure, the linear structure is defined with the help of iron to iron bond. Having iron to iron bond single bond in a linear shape, the structure is indicated as linear in geometry. Same to that, if you go for further more complexes such as dodeca-carbonyl tricobalt complex, dodeca-carbonyl triruthenium complex, if you go, right. So in this, the three rutheniums having 3 metal to metal bonds in direct, and has 4 metal to carbonyl ligand bonds, terminal metal to carbonyl ligand bonds, right. Where here the structure of complex of cluster is trigonal, where the trigonal structure of trigonal is defined with the help of ruthenium to ruthenium 3 bonds. With the help of ruthenium to ruthenium 3 bonds, it is defined as trigonal structure. right? The structure is never defined with the help of metal to ligand bond. The structure is defined with the help of metal to metal bond. Such when it giving an structural, physical, chemical importance, then thus the complexes will be said as metal clusters, right? Where in this particular complex dodeca carbonyl ruthenium 3 structure, triruthenium structure, it is having a metal to metal direct bond, and there are multiple rutheniums, and it is a metal complex where metal and carbonyl bonds are existing, right? So complex existing metal to metal direct bond and having metal to metal direct bond importance, where it is suggested by the structure, where it is giving the structures, right? Metal to metal bond giving the structure, then thus the complexes will be called as metal clusters. Like this, the metal clusters are having the definition, right? So now we have to move on for classification of metal clusters. Classification. When it comes to the classification, the metal clusters are classified into two types. Metal clusters are classified into two types, right? Saying that low valency metal clusters and second are high valency metal cluster. Low valency metal cluster and high valency metal clusters. So what is the classification? What are the characters of low valency, high valency metal clusters are? The classification depends upon the oxidation state of metal ion. With the help of metal ion oxidation state, the metal clusters are classified into two types, saying that low valency metal clusters and high valency metal clusters. Low valency metal clusters nothing but the complex metal clusters having metal oxidation state in between +1 0 -1, +1 0 -1. The complexes, so the metal clusters, metal ion having 0 +1 -1 oxidation states, right? 0 or +1 or -1 oxidation state, then those metal clusters will be called as low valency metal clusters. Where it comes to high valency metal clusters, the metal ion in high valency metal clusters has much more larger oxidation states, such as +2, +3, +4 and so on, right? The metal clusters having more than +2 oxidation state of metals, then thus metal clusters will be known as high valency metal clusters. And coming to the low valency metal clusters, these low valency metal clusters also known as metal carbonyl clusters. Carbonyl clusters. Since most of the low valency metal clusters has ligand carbonyl, right? So which means low valency metal clusters will have ligand as carbonyl as ligands, right? So when that carbonyl is existing ligand in metal clusters, low valence metal clusters, when we observe the oxidation state, the carbonyl, as it is a neutral ligand, the neutral ligand of carbonyl never polarizes the metal atom to have, never polarizes to have large oxidation states. large oxidation states, right? Having so far nothing but the metal carbonyl clusters will have lesser oxidation state. It never polarizes, never generates more oxidation state onto the metal atom. So far these metal carbonyls are can be said as low valency metal clusters, low valency metal clusters. Coming to high valency metal clusters, high valency metal clusters also known as metal halide clusters, metal halide clusters. So why it has to call metal halide cluster? Because the ligand in high valency metal clusters are halides, right? Most of the time high valency metal clusters will have halides as a ligand, halides as ligands, right? So where the halides, what they does, as the halides are negatively charged ligands, they will polarizes the metal ion to more oxidation state, will polarizes more extension, where the metal ion will carry higher oxidation state on it. So so that the ligand halides, as they are suitable for the higher oxidation state metal clusters, so the halides existing metal clusters will be high valency metal clusters, where the carbonyl is suits for the low metal oxidation state metal clusters. So the low valency metal clusters will have chloride as an carbonyl as an ligand, right? And thus it will be called as metal carbonyl clusters. Low valence metal clusters are called as metal carbonyl clusters, and high valence metal clusters will be called as metal halide clusters, right? When it comes to the next characters of low valency high valency metal clusters, the low valency metal clusters are formed by later transitional metal ions or metals, right? It forms by the later transitional metals, right? Where it comes to high valency metal clusters are formed by earlier transitional metals. You know that what it means by earlier, what it means by latter, what it means by early, what it means by latter, at least that you know, right? Earlier nothing but it is what we can say, it is first, right? Latter nothing but it next, right? Final, right? So when we look into one sequence of transitional metal complexes, right, we know that scandium, titanium, vanadium, chromium, manganese, cobalt, and manganese, iron, cobalt, and nickel, copper, zinc. It is in third D series of the transitional elements, or first series of the transitional elements, where if we say that if we make it in this particular series into a half, exact in half, right, cutting in two halves, right, it would have first 5 elements and next 5 elements, right? If it is have like that, right? So when we look into these two, right, the from the iron to zinc, the oxidation states, if we observe stable oxidation states of these metal ions, iron has +2 +3 and cobalt has +2 +3, nickel has stable oxidation of +2, copper has +2 and lesser stable oxidation state of +1, zinc has +2, right? Where when we observe these metal ions oxidation state, it limited till +2 only. It limited till +2 only, right? Which nothing but it has lesser oxidation states, right? When it comes to the scandium to manganese, scandium it may go +2, titanium +3, vanadium +4, +5, and this may be +6 and +7. Chromium also has +6, like that. Vanadium has +5, titanium has +4, +2, +4, and scandium has +3. So first 5 elements having an higher oxidation states, right? Last the secondary 5 elements, if we observe, they has +2, +1, +3 lower oxidation state as stable oxidation states, right? So here the first 5 elements can be titled as earlier transition elements. They are initiating the series. So far they will be said as earlier transition elements. When it comes to the second series, second part of the series, they will be said as later transition elements, right? Because at the end, at the second part, they are coming. So they will be said as later transition elements. Where when we observe these particular later transition elements which having lesser oxidation state can easily forms the metal carbonyl clusters or low valence metal clusters, right? Where low valence nothing but what oxidation state should be lesser and lesser. So here the latter transition elements has lesser oxidation states as stable oxidation state, lesser oxidation state as stable oxidation state. So far they will form latter transition elements, latter transitional metal and metal ions will forms low valence metal clusters, whereas earlier transitional metals carrying more oxidation state, +5, +7, +4, right? So having higher oxidation state as in stable oxidation state, the earlier transitional metal ions will form high valency metal clusters or metal halide clusters, like that. The high valency metal clusters will be counts for the earlier transitional metal ions, and low valence metal clusters will formed by the later transitional metal ions, right? So this particular observations we can have in the two classifications of metal low valency metal clusters and high valency metal clusters, right? So here we go for next. Now coming to the each part of the classification, the first part when we go, as it is low valence metal clusters, and thus low valence metal clusters titled as metal carbonyl clusters, right? So coming to the metal carbonyl cluster, classification of metal carbonyl clusters. So, and this also has two types. Metal carbonyl clusters also has two types, right? And that is low nuclear carbonyl clusters, high nuclear carbonyl clusters. Low nuclear carbonyl cluster, high nuclear carbonyl clusters, right? Low nuclear carbonyl clusters, and second is high nuclear carbonyl clusters, right? And this particular classification actually depends upon the number of metal atoms or ions, right? Depending upon the number of metal atoms, the metal carbonyl clusters are classified into low nuclear carbonyl cluster and high nuclear carbonyl cluster, where low nuclear carbonyl cluster is nothing but the number of metals are restricting from 2 to 4, right? The metal carbonyl clusters having metal ions 2 to 4 will be known as low nuclear metal carbonyl clusters. The lesser number of metal ions is found as in metal clusters will be known as low nuclear metal carbonyl clusters. When it comes to high nuclear, nothing but the number of metal atoms, the number of metal should be more than 5 and more than 5, more than 5, right? 5 or more than 5 or more than 4 metal ions consisting, number of metal ions consisting metal carbonyl clusters is nothing but high nuclear metal carbonyl clusters, high nuclear metal carbonyl clusters, right? And looking to the 18 electron rule in low valency metal clusters, low nuclear metal carbonyl clusters, high metal carbonyl clusters, where low nuclear metal carbonyl clusters obeys the 18 electron rule. 18 electron rule will be obeyed by the low nuclear metal carbonyl clusters. When it comes to high nuclear metal carbonyl clusters, the 18 electron rule may not be obeyed, right? The reason is, since the number of metal to metal bonds sufficient number of metal to metal bonds are existing in low nuclear metal carbonyl clusters. So far, the 18 electron rule obeyed by the low nuclear metal carbonyl cluster, whereas in a high nuclear metal carbonyl cluster, the sufficient number of metal to metal bonds are absent, right? There will be deficiency in metal to metal bonds are existing in the high nuclear carbonyl clusters, right? So this is how the different classification of metal carbonyl clusters we can explain. And so from this we will going to have one part of metal carbonyl clusters initially, thereafter we will go for the next class, right? So initially we will go within low nuclear metal carbonyl cluster, thereafter we will go into high nuclear metal carbonyl clusters, right? So in low nuclear metal carbonyl clusters, here as it chapter covers, we will start with the structural aspects of trinuclear metal carbonyl cluster. Trinuclear metal carbonyl clusters. Trinuclear metal carbonyl clusters. Structural aspects of trinuclear metal carbonyl clusters. When it comes to general formula for trinuclear metal carbonyl cluster is dodeca carbonyl trimetallic clusters are said as trinuclear metal carbonyl clusters. And these trinuclear metal carbonyl clusters are formed by the metals such as iron group metals, iron, ruthenium, and what we have, osmium. Iron, ruthenium, osmium are the three metals is forming the trinuclear metal carbonyl clusters. When looking into the structure of these, in generally they has this type of structure. Three metal ions are bonded each other with three metal to metal bonds, and the 12 carbonyl ligands are in terminally bonding with each metal. 4 4 is the general structure. Where it come to an iron structure, dodecacarbonyl iron structure, it has slight deviation from the general structure. Where similarly with the general structure, the tri-iron structure, trinuclear iron structure has three metal to iron bond, where the ligand bonding is slightly different. The metallic bonds are same, metal to metal bonds are same, but when it comes to an metal to ligand bonds, it has slight variation. Where here it has two bridging carbonyls. Thus two bridging carbonyl never look into an first general structure, whereas in iron structure we will come to know two bridging carbonyl. In the general structure, where all the carbonyls are 12 carbonyls are in terminal, where it comes to an iron structure, there are 10 carbonyls in terminal, 2 are in bridging. That is the variation we can see. So when we write up the structure characters, trinuclear carbonyl dodecacarbonyl has 12 terminal metal to carbonyl bonds and 3 metal to metal bonds, whereas in triiron dodecacarbonyl triiron, it has 10 terminal metal to carbonyl bonds and 2 iron to carbonyl iron bridging bonds it has existing, and 3 iron to iron bonds are existing, metal bonds are existing, right? These are the particulars of metal clusters we can write, right? So when we observe the symmetry of these two particular structures, right, actually we have to indicate the structure, right? The structure as it is having an 3 metal to metal bond, as 3 metal to metal bond existing, the structure is trigonal structure. It has, in trinuclear metal clusters, the structure is trigonal structure. Where it come to, when we have to differentiate the two different structures in trinuclear as such, the metal with ruthenium and osmium are mixed metal ions. right? This is having particularly the iron structure specifically when there are three iron atoms are forming dodeca carbonyl cluster. It has two bridging carbonyls and 10 terminal bonds where it come to an mixed metal ions having forming an trinuclear structure, or ruthenium metal ion forming an trinuclear carbonyl structure, or osmium forming trinuclear metal carbonyl structure. It would be have 12 terminal structure, right? It has 12 terminal structure, and the way when we want to make differentiation of these two structures, these two types of structure, we have to go for symmetry. We have to go for symmetry, where when we look into the symmetry of the general structure, right, where there is no bridging, all metal to carbonyls are terminal. There we can say that all these having an trigonal structure within all three terminals of same three terminal trigonal structure it is, right? Having, it can be symbols as in trigonal with same three terminals. So with this same three terminal trigonal will have the symmetry of D3H, will has symmetry of D3H, you know that, right? Which similar to the BX3. You know that BX3 molecule will have D3H symmetry. So here, as similar as that, this particular structure also will have same D3H point group. And when it into this iron structure, when we want to look the symmetry, it can be it can be suggested as trigonal structure with two terminals same, one is different, right? This particular terminal where it having all four carbonyls in a terminal, where the other two terminal having three terminal and two bridging carbonyls. So for these two terminals same, and one terminal is varying with two other terminals, right? So this particular structure will have, right, C2V point, right? So thus the structural differentiation we can give with respect of symmetry. So symmetry of iron structure will be C2V, right? So that is how the structure of trinuclear metal carbonyl clusters. And when we go with the 18 electron count is, as we said, that low nuclear metal carbonyl clusters will obey the 18 electron rule. So here it is obeys this particular structures or not, we have to see 18 electron count, right? The formula is equal to, right, what? Valency electrons of metal ion plus valency electrons of metal ion plus number of electrons donated by ligand, here it is an carbonyl, that is what, plus or minus oxidation state and plus 2 into metal to metal bonds, 2 into number of metal to metal bonds. This would be the 18 electron count formula. So with this help, here the metals existing in the formula of M3O taken twice, otherwise you can say that tricarbonyl triiron cluster, where here when we look into the metal ion, the charge on overall cluster is 0, right? Nothing is existing, nothing but it would be 0, right? And the carbonyl, as we know that it is a neutral ligand, so it never counts for the any oxidation state. So this is not counting for any oxidation state, and overall the complex pair has 0 oxidation state, nothing but metal all 3 is counts for the oxidation state of all 3 will be counts for the 0. So 3 all getting 0, 1 each also gets 0, right? The oxidation state of metal will be 0. So with respect of that, iron or ruthenium or osmium, they are the D6S2 configured metal ions. So in valency there will be 8 electrons they have. So thus valence electrons of metal ion plus number of electrons donated by ligand. So into this is into number of ligands. So number of ligand donated electron, carbonyl can donate 2 electrons. Thus in multiple ligand number of carbonyls are what? 12. So plus or minus oxidation state, the oxidation state on coordination pair is 0. So that writing plus 2 into number of metal to metal bonds, right? How many metal to metal bonds are existing? Here there are 3 metal to metal bonds are existing. So far 2 into 3, right? Here in valency of electrons in multiple with number of metal atoms or metal ions. This is also we have to count. So 8 into 3, 8 3 is a 24, 8 3 is a 24. So now it would be 54. In total it would be 54, right? So actually the electron count is equal to valency electrons of metal ion into number of metal ions plus number of electrons donated by ligand into number of ligands plus or minus oxidation state plus 2 into number of metal to metal bonds, 2 into number of metal to metal bonds, right? This would be the formula. With that respect of formula, the number of metal ions are 3 and valence electrons of metal ions are 8 into 3, and number of electron donated by ligand is 2, number of ligands are 12 carbonyls, so far 12, plus or minus oxidation state is 0, coordination pair having a 0 oxidation state, plus 2 into number of metal bonds, 2 into 3 is the metal bond number. So that where 8 into 3 is 24, 2 into 12 is 24, 3 into 2 is 6. So in totally 24 into 6 is 30, 30 plus 24 is 54, right? 54 electrons for all 3 metal ions valence electron densities, right? So therefore when it comes for an each metal ion, metal valency electron density will be equal to 54 by 3. There are that comes to 18 electrons. So far here the 18 electron count is equal to 18, nothing but the complexes of trinuclear metal carbon clusters will obey 18 electron rule, right? That's it. The trinuclear metal carbon cluster structures. So here we will stop.